Hello. I've always loved music, but I never thought I would be a speaker. My name is Stephan Erasmus. I'm presenting some of the work me and a master student and under Prof. Campus guidance at Stellenbosch University in our electrical machines lab. So this project was largely funded by the National Research Foundation, and it's been coming a while. It's probably like 2-3 years in the process. A lot of students working on it. So I'll be presenting on as you can see, a small-scale geared turbine system with a slip-synchronous damping technology. I'll just go through. I'll explain a little bit of introduction, some of the components of the drivetrain, the performance simulation results, and some of our laboratory measurements. So, as I said, this project is coming along from the past 2 years, and it's basically we kept it kind of small. So we kept it 2.2 kilowatt and downwind. So the wind is coming from the back, and as you can see, we built one last year. So this is not it. This is last year's one, and we've got absolutely crazy nacelle. Especially for a downwind. We're actually addressing that now this year. But and this is the design for the next one. It has a nacelle, although it's not on there, and it looks a lot better. It's a grid-connected technology, but also with mechanical damping. I'll get to that shortly. So it's based, or the aim of it is it's small scale for rural, urban, suburban applications. Although like we designed for 2.2 kilowatts, it's easily scalable to up to 80 to 100 kilowatts. It's very robust, and it uses minimal power electronics to generate electricity or to harvest energy. So first off, we have the turbine blades. What we used was a 1.8 meter radius blade with a power coefficient curve, as you can see at the bottom. So we chose it at about optimal fixed speed of 9 meters per second, yielding about between 2 and 3 kilowatts. What we have is tower shadow from torque pulsations, because it's a downwind machine, and So we also have a gearbox right behind the blades. It's a single-stage helical gear unit, and it's an up-speed gearbox, so with a gear ratio of about 4, and the efficiency we measured about 97% at 130 Newton meter. The next part is where the innovation comes in. So we have a permanent magnet slip coupler. It's a machine that consists of two rotating parts. You have a permanent magnet part, and you have short circuit coils on the other end. This coupler, both of these rotor, as I said, rotate, and it kind of functions a bit like an induction machine. So any pulsations or ripple that you will see on the blade side, the gearbox will transfer to the gearbox, will all be filtered out by this coupling. As I said, it's mechanical, so it's very robust, and it operates at an efficiency of 97%. A bit more detail on it. The coupler is 28 by 30 pole slot combination, and it has 30 non-overlap short-circuited coils. There's the physical construction of the permanent magnet coupling, and we use the permanent magnet synchronous generator on the back end of it to generate electricity. This was also built in-house by a final year student. So we retrofitted it inside a standard casing, and as you can see, it's permanent magnets on the other side, and then wound rotors, wound stator on the other end. 10-12 pole slot combination, and here's some of the technical aspects, but it's a pretty standard generator. Then the final part of the drivetrain component, or part of the system actually, is the grid side. So we aim to try and connect it to the grid by using a very basic, robust grid connected controller. So it matches the frequency and it locks when it's at synchronous frequency. We've tested it with like the slip or this damping technology a few times and also measured it against the grid code, and it does pretty well. To get into more of the detail parts, this is our analytical model that we set up to get into more of the control part in the dynamic responses. So here's the PMSG modeled. As you can see, this side is the rotor side and the other side is the stator side. Our dynamic equations, excuse me for that, dynamic equations of the system or the model. The permanent magnet slip coupler is just modeled as a gain, and then drivetrain, we have the inertias on the model, and then modeled into the complete system like that. So this part is a synchronous generator, slip coupler here, and some rotor dynamics here, and shaft dynamics here, and then you have the blade with the incoming wind speed. So on this side we can input now a wind profile, and we can see what kind of dynamic response we measure on the other side. Here's some of the components or the values of the components that we measured. So there's a ramp response, so you can see it's under damped response, and also the current out is about 5 amps AC. The dynamic performance is, so this is where the interesting damper comes in, because the damper can filter out a certain kind of frequency. So we try to find where's the cutoff frequency for this. So the simulations, we estimated around a magnitude of between 2.5 and 8 hertz, or between 4 and 8 hertz, filtering out everything above 8 hertz. Here you can see it in the simulated talk. Right. This is our test setup. So once again, we have the physical components and we model the wind. We have a wind profile. We have an inverter connected to a induction machine that provides just the wind profile, so we can see the response on the other end. Here's the gearbox, slip coupler, and the permanent magnet synchronous generator. First off, we have our step response as well as our current. And as you can, I don't know if you remember the previous slides, but it's quite on par with what we've simulated. You can also notice that we have a 5 amp. The current is 5 amps and the torque, the current is 5 amps and the torque is 145. Here's the filtering capability of the system. So there's 8 hertz. We put in a frequency of 8 hertz and simulated versus measured. So measured results are a bit choppy, but there's no frequencies coming through from which we put in to what we put out, compared to lower hertz, where you can actually clearly see the torque passing through, or the current being affected by the low frequencies.